discuss the conditions that need to be fulfilled for synchronizing a generator, let's say with the bus. In this particular case, the bus will be, or the WAPDA, the supply from the WAPDA will be acting as a bus. So this is basically a sort of schematics is shown here, where this block represents the synchronous generator. This is the armature connection, a three-phase connection, and we also have a field to the rotor windings of the synchronous machine. And we discuss in theory, we have to supply the rotor with a DC current. So this is synchronous generator, this is the stator, and we will feed the rotor with a DC current. Now, since we know that synchronous generator should be run by means of a prime mover, so in this case, the prime mover or the DC motor, a shunt type DC motor, will act as a prime mover which will run the, or which will rotate the rotor of the synchronous generator. So we feed it with a DC current, and at the same time, by means of the shunt connected DC motor, we rotate the rotor. So this is the sort of circuit, and this is the WAPDA. The WAPDA is shown here, and this is shunt type DC motor where we have an armature supply, and in order to vary the field current, because the armature and the field, they are connected to the same supply as it is shunt type, so we will vary the field current by putting a resistor in the field circuit. So this is basically the circuit. The DC motor will act as a prime mover, and this is the synchronous generator, and we have to fulfill these conditions. We discussed it in the theory. What we are supposed to do? We have to control the prime mover in order to accelerate the rotor. So we have to control the prime mover in order to accelerate the rotor. Another thing we need to do is to magnetize the field. We are supposed to magnetize the field of the synchronous generator, and at the same time we need to run the rotor. So control the prime mover by means of this DC shunt type motor, magnetize the field from a DC source, make V of the generator to that of the system. So make the V close to the system, and once we achieve it, then connect it. So these are the steps. This is the circuit, and the line shown here, the line shows here the WAPDA. So now another important thing is that we discuss it even in the theory, to make the V, which is the terminal voltage of the generator, because we know that once the rotor rotates and we also feed it with a DC current, it will induce voltage on the stator windings. And we also have another quantity, what we call the terminal voltage. Between these two quantities, one is the induced EMF, one is the terminal voltage. We discuss it in the theory that there is also a drop across the synchronous reactance of the machine. So the induced EMF, we know that it is related to the derivative of the flux, and here the induced EMF can be varied either by varying the field current or by varying the derivative. So the flux can be varied by means of the field current, and the derivative can be changed by changing the speed of the synchronous machine, that of the rotor. So if we did say now, the speed can be changed either by increasing the voltage, because we know that changing the voltage to the DC motor, or let's say increasing the voltage, one of the methods of increasing the speed of the DC motor is to increase the voltage. So by increasing the armature voltage, the speed of the DC motor will change, and in this way, since the synchronous generator is connected to the, the DC motor, and the rotor of the synchronous generator is connected to the same shaft. So by increasing the voltage, the speed of the DC motor will increase. This will increase the speed of the shaft, and it will also increase the speed of the rotor. Another way of increasing the speed is by means of the field current. And if you remember, we discussed that in the theory, that in the beginning, let's say we increase the speed of the DC motor, that of the shaft, because both are connected. So in the beginning we increase the voltage, and once we reach the rated voltage of the armature of the DC motor, in order to further increase the speed, because we can't change the voltage anymore as it is the rated voltage, we then decrease the field. Meaning to say we decrease the flux, and we know that by decreasing the flux, the speed will increase. So these two options will be used. One is by increasing the voltage first, reaching it to the rated voltage, and then if you further want to increase the speed of the shaft, we decrease the field current. So by these two methods, we will change the derivative of the flux. We will increase or decrease its induced EMF, and correspondingly we will change the terminal voltage. And once we achieve the voltage of the generator equal to that of the system, we will then connect it. So once we connect it, we called it synchronization of the synchronous generator. So that discussion which I have carried on the board, and now I will demonstrate it to you with the help of the circuit diagrams, or we will practically do it in order to make it more clear to you, or to make the synchronization of the machine or generator to the WAPDA, I mean to make this understanding more clear to you. So let's go to the circuit diagram. So this is basically the circuit diagram. We have here the connection from the WAPDA. This is the connection from the WAPDA. And here, this is basically three-phase supply. We have a wattmeter here, and here is a war meter, because you know it's a this is the AC system, so both the power will be associated, active power and reactive power. So this is the three-phase supply from the WAPDA. This is connected in series with the wattmeter and with the war meter, and these two, the connection of these two meters, these two are in series with the connection from the WAPDA, and further it is connected to another module, what we call synchronization module. So here we have the three-phase supply from the WAPDA. The down supply, which is this one, these three lines, it is coming from the synchronous machine. So this is basically the down supply here is coming from the synchronous machine. So this is basically Y connection. This is the armature of the synchronous machine. This is the field of the synchronous machine. And as I have discussed on the board, that this is the DC supply. So here this DC supply is connected to the rotor, and this is a fixed supply. We have here two possible ways of supplying the voltage. One is fixed supply, one is variable supply. So we are connecting here by means of these two connectors. We connect the fixed DC supply to the rotor of the synchronous machine, and we will vary the field current by means of this exciter. So moving the node will change the field current. So by means of the exciter we will change the field current, and it is connected to a fixed DC supply. Now further, because I mentioned that the synchronous generator should be run by means of a prime mover, and I discussed that the prime mover here is the DC shunt type DC motor. So here this connection is the armature connection, and as one can see here that the field where we have also a rheostat or a variable resistor connected in series with the winding. So these two are in parallel. One can see here. These are the two connections coming from the variable supply, because I mentioned there that we will change the speed of the DC motor by means of either varying the voltage or by means of varying the field. So the armature is connected to the variable voltage source, and this is in parallel to that of the field winding. But we also put a rheostat in the field winding in order to vary the field current. So this DC motor will act as a prime mover for the generator. So this is the circuit, and here the synchronization module. In between the supply from WAPDA and that from the synchronous generator, there are three lamps shown here. This method, I think it's called dark lamp method. So, dark lamp method, yeah. Okay, so this is basically a dark lamp method. These are lamps, I believe. So we will show now that for achieving synchronization, as I mentioned there, we have to make V of the generator close to that of the system. So for making it close to that, I discussed basically before even the four conditions. One is to make the V of the generator I mean, to make the V of the generator close to that of the system, 4 conditions should be fulfilled. One is the same phase order, one is the magnitude of the voltage, one is the frequency, and one is the phase angle. So once we will achieve the V of the generator, close to that of the system, we will turn this button on, and then the generator will be synchronized with that of the water. So let me fulfill those conditions now. We will make V of the generator, close to that of the system. And to make it close to the system, I once again repeat the words that we have to fulfill those 4 conditions. So now let me start the experiment. So here one can see that basically here we will also measure the voltage. So this is the, if one look here, this is the WABDA, and here we measure the voltage of the WABDA, that is line to line voltage. So by turning the module on, one can directly see here the voltage is coming from the WABDA, but still we have not basically run the synchronous generator. So the voltage from the generator, the voltage is 0. One can see here quite clearly. This is the voltage where we measure it to, I mean, we here measure the WABDA, the voltage of the WABDA, and here we measure the voltage of the generator. So the WABDA voltage is measured here. It is around 400 volt, and that of the generator is 0 because we have still not started the generator. So now let's make this V of the generator close to that of the system. So what we will do now, we will initially increase the voltage to start the DC motor. So one can see here now, the motor is started, and at the same time it starts the synchronous generator because both are connected to the same shaft. So let me move it to 220 volt, which is the rated voltage. And one can see here, we increase the voltage and the speed of the machine, it increases, because by increasing the voltage of the DC machine, this is one of the methods of increasing the speed. So by increasing the voltage, the speed increases, as you can even hear from the voice. So let's first move it as I even discussed there, that first we increase the speed by moving the voltage to the rated voltage. So I will first make it the rated voltage. The speed is increasing, and even one can see here that by increasing the speed, we achieve now the induced EMF and also the terminal voltage. So here now we are basically achieving some voltage also of the machine, but because here it is not close to that of the system, one can see here that the lamps are on. There is light in the lamps. So once we will achieve the V close to that of the system, the lamps will turn on. So let me first move it to 220 volt. Or I think we keep it a bit lower and we change the filter. 210, okay. So let's move it to 210. You see here, the voltage is 210. But still, the voltage of the generator, that of the generator, this is the voltage of the WABDA, which is above 400 volt, and that of the generator is less than 400 volt. So, and you can also see the blinking of the lamps. So it means that synchronization is not yet achieved. So now what is the other option? We have to increase the speed of the prime mover by means of varying the excitation of the motor. No, but I mean we have to vary the speed. So let's now increase the speed by means of now increasing the field of the or varying the field of the motor. So this is the motor. So as I mentioned that we first increase the speed by means of increasing the voltage, armature voltage, and now we will increase the speed further by means of decreasing the field. So here is the rheostat. On this side one can see that the resistance is maximum, on this side the resistance is minimum. So by pushing the knob toward this side or by moving it to this side, it means that we are increasing the resistance. Okay. One can see here, as the speed is increasing, the voltage is getting closer to that of the system. Okay, so let me explain even what we were doing actually. We were also changing the field of the man machine, because I mentioned there, if you want to achieve the voltage of the generator, close to that of the system voltage, we can also vary the field current. We change the voltage, this voltage, either by increasing the speed, which change the derivative, or we also change the excitation of the field, the man field, which also change the flux state. And in these two ways, we basically change this voltage. So now you can see here, the blinking of the lamps is almost, there is no blinking. You see here? So once we have no blinking, it means that the voltage from the generator is equal to that of the system voltage, because if there was supposed to be any difference of the voltage, we would have we would have the blinking of the lamps. Okay, even one can check the phase sequence. Yeah, one can change the phase sequence. So we discussed that 4 conditions need to be fulfilled. The 4 conditions also include the phase sequence. So let me change the phase. You see, there is no blinking. Okay, so if I change the phase sequence, let's say, you see here, if I change the phase sequence, one can still see the blinking of the lamps. I just changed the 2 connections of the machine, and one can see now the blinking of those lamps. So it means that the phase sequence are not the same, and we have to achieve all those 4 conditions: same phase sequence, same phase order, same frequency, and same phase angle. And once these 4 are achieved, there will be no blinking of the lamps. So now let me put it back to the same position. So you see now, no blinking of lamps, and it means that now the system, the voltage from the generator is equal to that of the system voltage. So now I will turn this button on, and now this synchronous generator is connected to the system. So this is basically the synchronization of the synchronous generator, or that of an individual generator, to that of the system. So with the help of this demonstration, where I talked about that, let me even conclude it or summarize it, that we have a synchronous generator. We need to run this synchronous generator, so we run it by means of a prime mover, and the prime mover here is the shunt type DC motor, where we have a armature connection, also the field connection. The field is connected, there is a resistance in series with the field winding to vary the field current, and here we have a fixed DC supply that is connected to the main field winding. This is a DC, and this is the armature of the machine, which is 3-phase AC, and this is Y connected. So I discussed that, or we demonstrated to you, we in the beginning increase the speed of the shaft by increasing the voltage, and once we achieve, let's say, a voltage closer to the rated voltage, we further increase the speed by decreasing the field flux, by decreasing the field of the DC shunt type DC motor, because by decreasing the speed will increase. And we also demonstrated to you that the voltage of the generator can be varied either by changing the speed or that of the field, that of the main field of the machine. So we also changed this field, and then we brought the voltage of the generator, of our generator, close to that of the wabda, and we demonstrated to you here. And once we achieved that the voltage is the same, because there was no blinking of the lamps, we also changed the sequence, and then you also saw the blinking. So if there is no blinking, it will indicate that there is, the conditions are fulfilled, where the phase magnitude is the same, the frequency is the same, the phase order is the same, and also the phase angle is the same. So once we achieve that condition where there is no blinking of the lamps, then synchronization is achieved. We turn the button on, and then the generator is now further connected to the, or it is connected to the system now. And one important statement here: once it is now connected to the system, I discussed that even before, in the course before, that once this synchronous generator is now connected to the system, it is now the slave of the system. What does it mean? I will basically demonstrate it to you in the next demonstration. So thank you very much for your attention. Assalamu alaikum wa rahmatullahi wa barakatuh. Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome back, dear students. In the first session, we demonstrated to you the synchronization of a generator with the wabda, and we demonstrated that after fulfilling the conditions where the terminal voltage is close to that of the system, then we can connect it with the system. But for making it close to the system, these four parameters need to be achieved, which is, one is the magnitude of the voltage, one is the frequency of this voltage, one is the phase angle, and one is the phase sequence. So after making it close to the system, we connect it. So that is then synchronized. But now, once synchronization is achieved, then even if we vary a couple of parameters, what happens? As we talk in the theory about bus connected synchronous machines. So here now I will talk about the two conditions: before synchronization and after synchronization. So what will happen if we vary a couple of parameters? So before synchronization, if we vary the induced EMF, we know that the terminal voltage will change. I will even show it to you, and we will demonstrate it to you. And this field, the induced EMF can be changed either by changing the speed of the prime or by changing the flux, which is related with the field current. So by changing either the speed or the prime mover, which we show or we demonstrated to you that we basically use the DC shunt type DC motor as a prime mover. So by changing the speed of the motor, we change the derivative, and in that way we change the induced EMF. The other way we change the flux was the field current. So by changing either these two quantities, the induced EMF changes, and if the induced EMF changes, it means the terminal voltage will change. So this is before synchronization. But what happens if once we achieve the synchronization, we connect this generator to the wabda, to the system, what happens afterwards? So now we will demonstrate. I will theoretically talk about it. Even I discuss it in my lectures, but I will once again refresh your memories. So what we will do? We will change the field current before and after synchronization, and then you will see what happens. And I will change the prime mover power. The prime mover in this case is the DC motor. And changing the prime mover power, what will happen then? So let's talk about variation of both these parameters before and after synchronization. So as we know that the power, the shaft power is the product of torque and omega. So once we connect it to the system, then the speed will remain the same. And by varying the prime mover power or by changing the power of the DC motor, you will see that the active power will change because speed is constant, torque will change. So let's talk about the variation of these two parameters and demonstrate it to you that what will happen if we vary it before and after synchronization. So let's now move toward the circuit and let me demonstrate to you. And even before going there, I will also remind that after synchronization, after connecting this machine to the Wabda, if we vary the field current, we talked about the fact, or we talked about the V curve. The V curve was the curve between the armature and the field current. And if you remember, we talked about three regions. One is under magnetization. This is under magnetization region. This was the condition when the cos of the pi was equal to 1, and this was the condition we talked about overexcitation. So this was overexcitation, this was underexcitation, and this was the unity power factor condition. By varying the field current after this machine is connected to the bus, what will happen if we vary the field current? So I will show to you now that once it is connected to the system and then if we vary the field current, you will see that the terminal voltage will remain fixed and only the direction of the reactive power will change, because we talked about the sensitivity of the reactive power to the difference of the voltage, and it's a generator, so this will be the difference of the induced EMF minus the terminal voltage. If we have overexcited case, meaning to say that the induced EMF is more than the terminal voltage, because we discussed it that in the overexcited case, whether it's a motor or it's a generator, the induced EMF will be more than a terminal voltage. So if it is overexcited case, you will see that the generator will provide reactive power to the system. And if we reduce the field current, bringing it to a position where the terminal voltage is more, because this is fixed after connecting it to the system. So this is fixed, we can vary this quantity after synchronization. So if we move it to the underexcited case, then this quantity will become smaller than this one, and then the reactive power will be fit to the generator, meaning that the generator will consume reactive power. But once again, the change in the direction of the reactive power, whether it provides reactive power or it consumes reactive power, generator remains a generator. So that will not change the nature of the machine. But afterwards I will even demonstrate to you that, let's say, if I remove after synchronization, if I connect this synchronous generator to the Wabda, and then I remove the prime mover, because prime mover in this case is the DC machine. So what will happen if I remove the prime mover power? Because after synchronization, this machine will be connected to the Wabda. So even if I remove the prime mover power, still this is connected to the Wabda. So then what will happen? That because now prime mover is available now, so the power will move in this direction now, because the prime mover power is 0. And then it will act like a synchronous motor, because if we remove the prime mover and it's still connected to the Wabda, it means that the direction of the current will change, because we are feeding it with now 3-phase current. And once we feed it with the 3-phase current, it means that the stator will produce a rotating magnetic field and it will lock the rotor and then it will run. But in this case now the power is provided by the Wabda, by the bus. So this will, after removing the prime mover, the Wabda will provide the power, and you will see that the needle will move in the opposite direction, and then this machine will act as a synchronous motor. So I will also demonstrate it to you. So let's now move towards the circuit and showing to you that what will happen before and after synchronization by varying the field current and by varying the prime mover power. So I hope the theory is now clear. I even talked about the theory in the lectures. So now let me demonstrate to you this concept with the help of the demonstration. So let's move toward the circuit now. This was the circuit that even we demonstrated to you the synchronization with the help of this circuit. So this is the same circuit. We will not once again go in detail into the operation, but quickly we will synchronize it, and then we will demonstrate to you the other concepts. So now this is the WAPDA supply. This now okay, first turn it on, and then you will see that by increasing the voltage, the speed increases. Also you can see the blinking of the lamps. We discussed it before. This is WAPDA, this is from the synchronous generator. So as long as we have blinking, it means that the system, the voltage of the synchronous generator is not equal to that of the system voltage. So we have to sort of make the blinking, we have to make it in a condition where there is no blinking anymore. So let me increase the voltage. You see the speed is increasing by increasing the voltage. It is still blinking. Okay, there is still some blinking. So you see now that the synchronous voltage, the voltage of the synchronous generator has become almost the same as that of the WAPDA. So now let me, but even before that, let me show you another important thing. Now let's say this is the field, this is the main field of the synchronous generator. This is the field. So now if I change the knob of the exciter, if you look here, the system, the voltage of the WAPDA and that of the system is more or less the same. So now if I let's say change the excitation, you will see this voltage will vary because I have not yet connected it to the system. So if I change, let's say, the excitation, you will see, you see, this voltage is fixed because it is WAPDA. This varies. You see, if I reduce the excitation, the voltage decreases. This is quite clear. You see, the voltage reduces. And if I increase the field, you see the voltage increases. So let me bring it close to the system voltage. I believe now, yes. So now you see that before synchronization, before connecting the generator to the WAPDA, by increasing the field or by decreasing it, the magnitude of the induced EMF and correspondingly that of the terminal voltage, it changes. So now there is no blinking and we can turn the switch on. So now this synchronous generator is synchronized with the system. Pay attention to these two meters. You can see that the var as well as the watt is approximately 0, meaning to say that neither the reactive power is flowing. There is no flow of reactive power because it is 0, approximately 0. Also the watt is 0. Why it is 0? Because we discussed in the theory that the reactive power is sensitive to the difference of the voltage. And since now the voltage of the generator, it is same or it is close to that of the WAPDA voltage, meaning to say there is no difference of the voltage. So what should be the reactive power flow? That should also be 0, which is quite clear here. Also, because we talked about that the system voltage and that of the synchronous generator is the same when even the phase angle is the same. And since the two voltages are the same, it means there is no phase angle difference. So that's why, because the active power is sensitive to the angle between the induced EMF and the terminal voltage, because now the two voltages are the same, and these are phasor quantities, and phasor quantities will only be the same when the magnitude as well as the angle is the same. Since these two are the same, now meaning to say there is no angle even between the two quantities. So that's why active power is also 0. I believe it is clear now. The difference of the voltage is 0, that's why reactive power is 0. Angle is also 0, so active power flow is also 0. So now we have talked about even the two powers. Now let me move towards the point where if I now change the field excitation, what will happen? So let me demonstrate that to you. This is the man field. If I change the man field after synchronization now, because I discussed that before synchronization, if I change the field, the terminal voltage of the generator changes. But now when it is synchronized, if I now change the field, what happens? We discussed it in the theory that if we have a low field current, it is under excited condition. So now let me move the field towards the lower side, meaning to say that let's reduce the excitation. If I reduce the excitation, we will move towards the underexcited case. And underexcited case is that case where the generator because the terminal voltage is fixed now, it will not change. But what will change is the induced EMF. So if I now reduce the excitation, the induced EMF will reduce, and if the induced EMF reduce, it means that the machine or the generator will now consume the active power. So look here, if I reduce the excitation, one can see here, you see the reactive power flows in that direction and it indicates the consumption. If it moves in that direction, it indicates consumption. There is no change on the active power. You see, if I change the field current, there is no change in the active power, only the reactive power changes. And if I further reduce it, one can see the consumption increases because the terminal voltage is fixed. As it is connected now to the system, the induced EMF reduces, and the more it reduces, the more will be the reactive power consumption. So this is under excited case. Now let me increase the excitation. If I increase the excitation, you see, I move to a point where the reactive power is 0. What is that point? This point is, we called it unity power factor condition, when the reactive power consumption is 0. And if I further increase the field current, you will see that the reactive power now moves in the other direction, or it becomes positive, meaning to say that now the induced EMF is more. It is overexcited case as we have increased the field current. So now this synchronous generator provides reactive power to the system. And one can see here, there is slight, the active power is positive. Because by changing excitation, the active power should not change. This must be in the other direction, meaning to say that because a generator should provide active power to the system. So the active power is positive, or it is almost 0. It does not vary with the field current. It must be positive because it's a generator. So by varying the field after synchronization, the generator still remains the generator. All that change is the reactive power. If we make the excitation lower, meaning to say if we keep it in underexcited case, the reactive power is consumed, and if we move it, or if we make the excitation overexcited, or if we increase the field current, we make the overexcited case, then the reactive power is provided to the system. You see, if I increase the excitation, the reactive power is provided to the system. So now we have demonstrated the case of varying the field current before and after excitation. So the reactive power changes only. Now another statement that I should make here, that even I discussed that, or I talked that after the synchronization, this machine will be the slave of the system. It can't do anything. It can't. The speed will remain the same. So now we have talked about the field variation, and let me talk now about the changing the prime mover power. How can we change the prime mover power? Either by means of the DC voltage, by increasing the DC voltage of the DC, by increasing the voltage of the armature, or by reducing the field flux. Because either by reducing the field flux, that of the prime mover, that of the DC motor, if we reduce the field of the shunt DC motor, the speed will increase. But because it is connected to the system, the synchronous speed must not change. Otherwise, it is not a synchronous machine. So, if I reduce the field now, that of the prime mover, I am not talking about the field of the synchronous machine. I am talking about the field of the shunt DC machine. So, if now I reduce the field, the speed of the prime mover must increase. But because now it is a slave of the system, it will not allow this the machine. The system will not allow the machine to increase its speed. But what will happen? That you will see now. If I now reduce the speed, so if I reduce the field, you see that the active power changes. You see here, if let's say, let me bring it back to that position. You see, by reducing the field, because the prime mover now want to increase the speed, but since it's a slave of the system, it will not allow the individual generator to increase its speed. Instead, what happens, that the power will increase. You see, so by now increasing the prime mover power, the speed remains the same, and the machine will provide active power to the system. Now it is quite, and the reactive power is more or less the same. It does not change. So now let me further reduce the prime mover or the flux of the DC motor. So if the flux reduces, the prime mover power will increase, and you see now the generator provides active power to the system. The reactive power hardly changes. And if I do it now, let's say the other way around, if I reduce now, let's say the power to the prime mover, what will happen? Now you will see that if I reduce the prime mover power can be reduced either by increasing the flux of the shunt DC machine or by reducing the voltage. So now let me reduce the voltage. You will see, please pay attention to the active power. I reduce the voltage, the armature voltage. You will see that now. If I reduce the armature voltage, one see, and now even the active power has moved in the other direction. You see. So now it means that now let's say now I have, you see, the prime mover voltage is 0, which means that the prime mover power is 0. But since now this system is connected to the WABDA, the connection is still there. Even the prime mover power has been reduced. It has been reduced to 0 now. But since this connection is now there, what will happen? That now the system will provide active power because it is slave of the system. What it says to the system, what it says to the generator, keep yourself with us, we will provide power to you. So now the system provides power to the generator, and one can see the direction of the active power here. It is now negative. It is now consuming, this generator, synchronous generator is now consuming active power. So if it starts consuming active power, it is no more a generator. What is now the nature of this machine? It is load, because we know that the load consumes active power. So if it now starts consuming active power, it is no more a generator, but it is still there with the system, and it is now acting as a motor because it is consuming active power. So this is basically the demonstration of changing the field current. We initially changed the field current, and I demonstrated to you that the reactive power changes. There is hardly any change in the active power. And if we change the prime mover power, the reactive power is more or less the same, only the active power changes. If we remove the prime mover by reducing the DC voltage to 0, then the system provides active power to the machine, and it is no more act as a generator, rather act as a motor. So now let me once again provide the prime mover power, and you will see that the active power, it changes its direction. So now it is again acting as a motor. Sorry, it is again acting now as a generator because now the prime mover power is there. And if I increase the prime mover power, you see, the active power production increases. Now this is the demonstration. We have demonstrated to you both the variation. I mean, we have demonstrated to you the conditions when we vary the field current as well as the the primer power. So we have demonstrated to you both these conditions. So now let me demonstrate one more case to you. Let's say if I remove the excitation of the synchronous machine, what will happen? Because we know that in a synchronous machine we have one part is armature, one part is the rotor. If I, let's say, remove the field, what will happen to the synchronous machine? Because it is connected to the system now. It is connected to the system, and if I remove the excitation of the motor, of the synchronous generator, what will happen? You will see that if I turn off the excitation, pay attention to the reactive power. You see, it has become now a large consumer of a reactive power, and that is basically the case when we have the induction machines. So induction machines or induction motors, it consumes a large amount of reactive power, as I have demonstrated that this machine is connected to the system, and if I turn off the excitation, let me do it again. If I turn off the excitation, it consumes a large amount of reactive power, and that is basically the indication that it is a induction motor. Because later on now I will talk about the induction motor, so I was thinking to give you even a sort of demonstration about that. So with this session now, we conclude our discussion, we end our discussion. We have demonstrated to you two important let's say facts, or we have demonstrated to you a couple of even concepts. We in the first session we talked about the synchronization. We demonstrated to you that how to synchronize the generator, let's say, to the system, and once we synchronize it, if we afterward change the parameters, so then what happens, or what happens to the active power, what happens to the reactive power. So now I hope with the help of the theory and with the help of these two sessions, I believe now the concept should be clear to you. And again, an important concept, that by changing the direction or by changing the sign of the reactive power, the generator remains the generator, the motor remains the motor. Only it either provides the reactive power or it consumes the reactive power, depending on whether we run it in the underexcited case or in the overexcited case. But the nature of the machine will not change. So with this session now, I end the discussion on the synchronous machines and rotating magnetic field. I hope you understand. I hope it will clear your concepts even more. And even I mentioned in the lectures that I will even arrange interactive sessions. So please watch these videos, two videos, quite watch it with attention. And if you have any queries, note it down. In the interactive session, I will even make it clear if something is still not clear to you. So please pay attention to the videos and note down your queries. So with this, now I end the session. Thank you very much for your attention. Assalamu alaikum wa rahmatullahi wa barakatuh.